Welcome everyone to this explainer. Okay, so if you've ever stared at a totally confusing string of numbers and letters, something like 1s2, 2s2, 2p6, and felt like you were trying to decode some ancient alien language, well, you are in the exact right place. Today, we are going to make complex quantum mechanics instantly intuitive. And how are we going to do that? Well, long before chemistry textbooks even existed, deep inside every single atom stood a magnificent, massive, and highly organized structure. We're going to call it the Grand Atomic Hotel. We are going to learn exactly how to check tiny guests, which we know as electrons, into this hotel. Because honestly, how these guests are arranged entirely determines how literally every single chemical reaction in the universe happens.
So here is our roadmap for today's explainer. We've got 1, welcome to the atomic hotel, 2, 3 rules of check-in, 3, mapping the periodic table, 4, noble gases in shorthand, and finally, 5, rule breakers and ions. Let's jump right in. Section 1, welcome to the atomic hotel. So imagine you are handed a chaotic, buzzing swarm of electrons. How exactly do you organize them around a nucleus so they don't just constantly crash into each other?
Well, we can actually translate these super abstract quantum terms into a familiar physical space. Think of the atom's main energy levels, or shells, as the floors of our hotel. Floor 1 is pretty small and cozy. Floor 2 is a little bit bigger. Floor 3 is even more spacious, and so on. Now, on each of these floors, we have rooms. In chemistry, these are what we call subshells and orbitals, and they're labeled with the letters S, P, D, and F. And finally, the guests checking into these rooms, those are our electrons. Every single electron wants a comfy place to stay, but this hotel is very tightly run. Section 2, 3 rules of check-in. We have 3 legendary managers who run this place, and they are incredibly strict. They dictate exactly where every single guest has to stay. First up, we have Manager Aufbau. Now, Aufbau is actually German for building up, and his rule is super simple. Electrons are frugal. They must absolutely always occupy the lowest energy room available first before they even think about looking at the higher floors. This means our guests have to fill the 1S room on the very first floor before they are allowed to so much as glance at the 2S room up on the second floor. You always build from the bottom up. Next, we have Manager Pauli, who enforces the famous Pauli Exclusion Principle. The crucial thing to remember here is this. Each room, or orbital, can hold a maximum of 2 electrons. Just 2. But there's a catch. If 2 electrons are going to share a room, they absolutely must have opposite spins. It's kind of like sleeping head to toe in a bed. This satisfies his rule that no 2 electrons can have the exact same set of 4 quantum numbers, meaning they can't have the exact same floor, room, and bed orientation. In quantum terms, 1 electron spins up, the other spins down. If they try to spin the exact same way, Manager Pauli kicks them right out. And our final manager is Manager Hund. Now, electrons have negative charges, right? Which means they naturally repel each other. They literally hate sharing. So Hund's rule dictates that when you have a suite of rooms that cost exactly the same amount of energy, like the 3 2p rooms on the second floor, the electrons are going to spread out. One guest goes into the first 2p room, the next guest goes into the second 2p room, and the third goes into the third. Only when all 3 of those rooms have 1 occupant will they finally, grudgingly, start to pair up. Everybody gets their own room first. Okay, let's actually see these 3 rules in action by checking in a carbon atom. Carbon has exactly 6 electrons. Step 1, Manager Aufbau says we gotta start at the bottom. 2 electrons check into the 1s room, spinning head to toe thanks to Manager Pauli, so that's 1s2. Step 2, the first floor is now completely full, so we move up to the second floor. 2 more electrons fill up the 2s room, that's 2s2. We have exactly 2 guests left. Step 3, we look at the 3 2p rooms. Manager Hund steps in and says, nope, spread them out. So the final 2 electrons take their own separate 2p rooms. That gives carbon an ending configuration of 2p2. Put it all together, and the final result is 1s2, 2s2, 2p2. Moving to section 3, mapping the periodic table. Now that you've got the rules down, I want to share a massive shortcut. You really don't have to blindly memorize the order of all these rooms. The periodic table is actually a literal blueprint of our Grand Atomic Hotel. What's absolutely fascinating is how the physical shape of the periodic table perfectly matches the hotel rooms we just talked about. See those 2 columns on the far left? That's the S block, and it holds 2 electrons. The 6 columns way over on the right, that's the P block, holding a maximum of 6 electrons. That sunken middle section, that is the D block,
with 10 columns for 10 electrons. And those 2 rows sort of floating separated at the bottom, that's the F block, holding 14 electrons.
And this brings us to the ultimate cheat code. You can literally just read the periodic table from left to right, top to bottom, exactly like you were reading a book, to write out the configuration for any element. The row or period tells you what hotel floor you're on. The block tells you what kind of room it is, S, P, D, or F. And by simply counting how many squares you move to the right, you know exactly how many electrons are checked into that room. Let's test this map out. Hydrogen is the very first square in row 1, sitting right there in the S block, so it's just 1s1. Carbon is in row 2, over in the P block, and it's the second square in, so its outer electrons are 2p2. Chlorine is in row 3, in the P block, and it's the fifth square in, so it ends in 3p5. But hey, a quick warning here. When you hit that sunken D block in the middle, the floor numbers drop down by 1 level. So even though you might be in the 4th row of the periodic table, the D block there is actually the 3D room, not 4D. It's an N-1 rule. Definitely keep that in the back of your mind.
Section 4, Noble Gases and Shorthand. As you start moving further down the periodic table, reading it like a book gets incredibly long and tedious. Luckily, chemists are not fans of wasting time, so we have this amazing shortcut that involves the hotel's absolute VIP guests.
The absolute magic number in our hotel is 8. We call this the octet. When an atom has exactly 8 electrons in its outermost floor, meaning the S and P rooms are completely filled up, it achieves perfect stability. The elements that naturally pull this off are the noble gases on the far right of the table. Because their floors are completely fully booked, they are perfectly stable and famously unreactive. They really don't want to gain or lose any guests at all. So, noble gas notation is our ultimate shorthand technique. We basically just bundle up all those perfectly filled inner floors, replace them with the preceding noble gas symbol in brackets, and then we only have to worry about writing down the remaining outer guests.
Let's look at calcium for a second. Writing out its 20 electrons the long way means writing 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. I mean, that's a headache. But if we just trace backward on the periodic table from calcium, the last noble gas we passed was argon, which has 18 electrons. So we literally just write argon in brackets, R, which accounts for those first 18 electrons. Then we just tack on what's left on the outer floor, 4s2. We've effectively boiled calcium all the way down to just its 2 active valence electrons sitting right outside that stable argon core. It is so much easier, right?
Section 5, Rule Breakers and Ions. Let's see how all this builds into real-world chemistry. While our 3 hotel managers are definitely strict, nature sometimes bends the rules in the pursuit of absolute stability. It's time to meet our rule breakers and see what happens when guests are forced to check out. Our very first major rule breaker is copper. Based on where copper sits on our map, you would totally predict its shorthand to be argon 4s2 3d9. But here is the secret. Atoms find completely filled subshells to be incredibly stable. Having that D room sitting at 9 out of 10 electrons is agonizingly close to perfection. So copper actually bends manager Aufbau's rule. It steals 1 electron from the 4s room and bumps it up to completely fill the 3d room. So the actual stable configuration is argon 4s1 3d10. Chromium pulls a really similar trick. We would normally predict it to be R 4s2 3d4. But just like a perfectly full room is stable, a perfectly half-full room is also highly preferred. So chromium just steals an electron from the 4s room to make the D room exactly half full. The true configuration becomes R 4s1 3d5. Nature is always going to prioritize that extra stability whenever it can. Now, what happens when atoms actually want to form chemical bonds? They turn into ions by either gaining or losing electrons to reach that magic VIP noble gas status. Non-metals, which are usually almost full anyway, will gain electrons. Metals will lose electrons to empty out their outer floors. But here is a massive, absolutely critical rule when you are checking guests out to make positive ions or cations. You must always remove electrons from the highest energy level, meaning the highest shell number, first. This trips up so many people when dealing with transition metals. Let's look at iron. An iron atom is Ra 4s2 3d6. If iron wants to lose 2 electrons to become an Fe2 plus ion, which electrons check out first? Well, you might think it's the 3d electrons because they were the last ones to check in, but remember the rule. You always remove from the highest floor number. The 4th floor is physically the highest shell, so iron loses its 2 4s electrons first. The final configuration for the iron 2 plus ion is simply Ra3d6. Always check out from the highest floor number.
So we've explored the ground state, the calm, stable, rule-following version of the atomic hotel. But I want to leave you with a final thought to chew on today. What happens if a photon of energy slams into our hotel? What if an electron gets so energized that it completely ignores the Aufbau rule, abandons its cheap room, and just jumps all the way up to an empty penthouse suite? That's what we call an excited state. And more importantly, what incredible chemical phenomena happen when that excited guest inevitably falls back down to reality? Well, that is a fascinating story for our next explainer. Thanks so much for joining me at the Grand Atomic Hotel.